Welcome back to the lab. Today we're going to talk about a component that limits inrush current but still allows massive quantities of power to flow. At least that's the theory. We implemented what is called a hot swap controller in our UPS. This device drives some N-channel FETs to slowly turn on a downstream DC load, and this hot swap controller continuously monitors the power delivered, and it serves as an electronic circuit breaker in case of a fault. We use this circuit for both its main function and some extra ones in our UPS project, and we're about to walk through exactly what our experience was while designing and testing this circuit. Before we get too far into this video, I want to take a short moment to tell you about something really exciting, and that's our latest design sponsorship. Check this out. Maybe you want to control something connected to mains, but don't know how to do it safely. We can help with that. That's what this contest is all about. Depending on the number of applicants, we will select between 2 and 5 winners. If you win, you'll receive up to $200 of materials, tools, and/or 3D printed parts to support your project, and no less than 4 hours of collaborative mentorship to go along with it. Not to mention, your project will be featured in one of our videos. There's no age restrictions except where prohibited by law. There's no country restrictions except where prohibited by law. Projects can be submitted by individuals or by teams. Okay, that sounds great. Here's how to enter. Tell us about yourself, tell us about your project, tell us how we can help. To enter, put the tag Design 2019 and a link to your video, post, or documentation in any of the comment sections for any of our videos released in the months of March or April. That includes this one. Best of luck. I hope you're as excited to work with me as I am to you. So thank you for watching EEforEveryone, and I cannot wait to hear about your next great project. To start this video off, we need to find the brains of this operation. We need to find what's going to actually do the decision making, and we selected a hot swap controller from TI. This part has electronic circuit breaker functionality baked in as a part of its core functionality. This part number is the TPS2490. This component was chosen primarily because of its ability to limit inrush current. After all, that is our primary design goal, but to implement this functionality with our controller, we needed to first carefully select a MOSFET, which is a voltage-controlled transistor. These transistors were sized so that they won't turn into a molten puddle of slag while absorbing the burst of power while driven in the triode or linear region while 50 amps flows through it. Not a small ask. In addition to the transistor, a specific network of passive components was selected to support the controller IC. These passives set specific timing and current thresholds. These passives end up playing a very key role in this circuit. They effectively set the current limit to pass while ramping on the downstream load, as well as the fault trip limit for the circuit breaker function. As we've discussed before, setting a maximum current and regulating to that while turning on a downstream circuit, now that's the primary function of inrush current limiting. After the downstream load has transitioned from fully off to fully on, the controller then clamps the high side switches on hard. This fully enhanced operation minimizes the steady state DC losses in our MOSFET while the system's operating normally. That last step is especially important in our design because we have 50 amps flowing through these FETs in the normal case. A couple milliohms will add up fast. The inrush current limiting action of the hot swap controller works great, and that can really extend the life of our relays by taking on the task of electrical switching. Why do relays fail while switching? Oh, I'm so glad you asked. Relays consist of mechanical contacts that physically close. These contacts are plated with a metal that has favorable characteristics for this application. It needs to be resistant to oxidation, have a low contact resistance, not be too expensive. There's only one problem. This is usually gold. And when voltage potential is applied across a very small air gap, a spark can jump across that gap. Since our relay is transitioning from not touching to physically in contact, at some point between open and closed, we're guaranteed to be close enough that an arc can be struck. The more current that's flowing through the relay, the more violent that arc tends to be. In extreme cases, the heat from this electrical arc can actually cause the two contacts to weld together. In lesser cases, this arcing will eat away at the contact material, eventually exposing the base metal. After the base metal is exposed, all bets are off. That metal will likely oxidize, quickly reducing the conductivity of that electrode, and therefore causing the relay to fail. This is especially the case for any sort of gold relay contact. There are other contact materials that don't mind arcing so much. Those are typically used when you're switching motors or in contactors, and others that require occasional arcs to actually keep the contact clean. This really depends on your specific relay, so you'll have to do a bit of research here. Thankfully, gold-plated contacts are pretty common, and that means that 8 times out of 10, arcing on your relay contacts is a bad thing. Making a bad situation worse, whenever a switch closes, the contacts vibrate or bounce off of one another a little bit after making initial contact. Think about this like a normal switch and the debouncing that we need to do to get a valid logic signal. This causes our relay contacts to make and break electrical contact repeatedly, not just once. Now that means that there may be a handful of small arcs eating away at the relay contacts every time it changes state. Now that's less of an issue when switching AC, since alternating current has 0 crossings periodically spread through the waveform. This means that if we're closing the relay at a random interval, odds are we won't hit the peak voltage and current all the time. Sometimes we'll switch almost nothing because we'll be in the 0 crossing. When voltage applied or current pulled through a relay is smaller during that switching event, this significantly reduces the severity of the arcing on the contacts. Yeah, so that's great, but we're using relays to switch DC, and not just any DC, we're switching up to 40 volts and 50 amps. This type of load would probably wear through our relay contacts in a couple thousand switching cycles. That's why we added the hot swap controller to our design. This will handle the electrical switching so there's no arcing in the relay ever. This gives the relays approximately the rated mechanical switching life, which can easily reach 1,000,000 cycles for a given relay. Now that's quite an improvement, a couple thousand to 1,000,000. So let's walk through the sequence of events that we need to do in order for us to take the full benefit of this circuit and never switch the relay electrically. This is the procedure that we need to follow if we want to leverage the full benefit of our hot swap controller. First, we'll cut power to the downstream load by disabling the hot swap controller. This will greatly reduce the current through the relays. In fact, it will bring it down to 0 amps. Now we'll actuate the relays to switch the other power source. This will connect either the primary or secondary power input to the input of the hot swap controller. We can now safely power on. So we'll enable the hot swap controller again, and this will ramp on the downstream loads at our maximum rated input current. Great, because our hot swap controller is what made and broke the electrical contact with the load before and after the relay changed state. This means that our relays will never perform an electrical switching cycle. They'll never switch while under load. Everything will be mechanical switching, or switching the relay contacts when there's no electrical load present. Mission accomplished. While extending the life of the plating on our relay contacts, this sequence also eliminates any concerns we may have about contacts welding together. Why? Well, it's pretty hard to weld without an arc. We removed all substantial arcing at the contacts by removing all substantial electrical load, and that means that we've removed the risk of welding our contacts together. That'd be pretty bad if we try to switch from one input to the other and the relay just doesn't move. So this plan sounds pretty awesome. It fixes a lot of problems with relays, but there's only one thing that we failed to consider when designing this gloriously complex solution. We could have just disabled the switch mode power supply that pumps power from the low voltage DC side to the inverter, and that would have reduced the load to almost nothing. Disabling that switch mode power supply would have effectively reduced the load down to 1 amp or less. This reduced current would have given us about 90% of the benefits of implementing the new hot swap controller circuit, but it wouldn't have cost us anything since we already have that enable signal. Not to mention, this would allow us to route the PCB in a more ideal way by not needing to cut up the power plane to stop at this relay. Removing this circuit would certainly reduce the overall footprint and cost of our design. Whoops. This is one of those situations that could have been resolved before the money was spent to build these boards if we weren't in such a rush. We didn't really need hardware in hand to take a moment, take a step back, think about architecture simplification options for our UPS. Thankfully, this feels more like a cost optimization thing and less of a deal-breaking mistake. It should work fine. It'll just take a little bit of the efficiency out of our circuit, and it's not a very clean architecture. This design could have been a little simpler, but if we get really sick of control, we can always just bypass the hot swap controller altogether with a shunt. A couple short jumper wires will do this nicely. Well, before we go and completely bypass the hot swap controller on our prototypes, let's not forget about its other functions. There's more here than just switching. The hot swap controller isn't only about switching something on in a controlled way, it also serves some other great functions. This doesn't need to be an all or nothing situation, right? There's still a couple more features that we'll get to use even if the switching of the hot swap controller isn't strictly necessary. The Inrush current limiting, an electronic circuit breaker, and an undervoltage lockout are all features that'll be nice to have. These features certainly provide some value to our system, even if they aren't core features. These are more quality of life improvements that add polish rather than nuts and bolts features, but let's take a few brief moments to discuss each of these on a high level and really dive into what they're adding to our system. The electronic circuit breaker is a particularly useful function of the hot swap controller. This controller is ultimately deciding whether or not power should be flowing to the downstream load, and it's doing this by constantly enabling or disabling a high side switch. In this case, that switch is a FET. This FET is a transistor capable of sourcing at least 50 amps to that load, and if we want the hot swap controller to enforce a current limit, we just have it monitor the voltage drop across a couple shunt resistors, and since we're working with so much current, we use 2.5 milliohm shunt resistors in parallel. The hot swap controller looks at the voltage drop here. When too much voltage is present across that shunt resistor, we know that too much current is flowing, and that serves as a flag. This tells the controller to drop the hammer and turn off the downstream load. This function would be pretty awesome because it allows for safe, resettable methods of setting a resettable current limit. A little redundant, whatever. But there's only one problem with this setup, and that problem is nuisance trips. A nuisance trip occurs when a protective circuit like a hot swap controller cuts power due to a fault condition that didn't really exist. For a fuse, there's something called an I²T rating that naturally averages out little transient events. Now, these are called nuisance trips because they can be a pain to completely eliminate. There are many factors that can lead to a nuisance trip, so mitigating all of these factors will surely be a challenge. We need to be absolutely sure that nuisance trips won't end up cutting power to our UPS unexpectedly. Every single nuisance trip will provide a new opportunity for data loss in the equipment connected to this system. That said, we really do need some overcurrent protection. Without any overcurrent protection, dangerous levels of current could be causing traces to melt off our PCB. There are hardware fuses that are correctly rated on the board to provide this basic level of not melting things protection, but something software resettable has obvious benefits. Another feature of the hot swap controller is the UVLO, or undervoltage lockout. While providing another mechanism to introduce nuisance trips, this prevents over-discharge of our connected batteries. This function requires an internal voltage reference and a comparator. These two elements are used to decide whether the input voltage is high enough, and by using a resistor divider, we can set the UVLO trigger point to any voltage we desire, as long as it's above that threshold. In this case, we set that threshold to 11 volts. This is the minimum input voltage we'd like to accept, and here's why. When the hot swap controller cuts out at 11 volts, this would typically indicate an insufficiently rated power supply being used to source the inverter, the input voltage dropping out due to a power outage, or a dead 2S lead-acid battery stack being used to source a lot of current into the UPS. Either way, it'll probably be best to not ask any questions and power down if this line has been crossed. That's why if a voltage less than 11 volts is applied, the hot swap controller is programmed to cut out and not reconnect power when the voltage rises above 11 volts. And that's without being reset, so it would flag our micro to switch to the other source and then try to enable again. Now, Inrush current limiting is a great feature of the hot swap controller as well, and it's one that's also pretty simple to wrap our minds around. Rather than turning on the downstream load as fast as possible, we turn it on with a constant current. We recently made a video that describes Inrush current limiting in depth, and if that sentence confused you, take a pause, check out this video, and come right back. The Inrush current limit that charges the downstream capacitive loads at our maximum output current in this case 50 amps, this constant current keeps things a little more reasonable, which should in theory prevent upstream circuits from browning out during load switch events. Awesome. So those words "in theory" reminds me of something we've seen in our preliminary testing. We've been having a heck of a time getting the circuit to function correctly. When we built up serial number 1, we didn't see any issues with the hot swap circuit because we always enabled the downstream boost converter and the hot swap controller at the same time. 9 times out of 10, works great. A couple nuisance trips, but nothing excessive. Serial number 2, on the other hand, whoo boy, nope, not even once. The second board we built up won't even power on without a shunt wire across the hot swap controller transistors. Despite not seeing this issue with the first board because we changed the power on sequence, whenever we enable the downstream power circuitry, this hot swap controller will either trip or reset. I haven't found the root cause for this behavior yet, so the path to fixing the issue isn't clear. At first, I was convinced this problem was with the current shunt monitoring. That turned out to be incorrect since I've disabled both the UVLO function and the current shunt monitoring, but the darn controller still trips out. My latest running theory is that there's insufficient bulk on the output of our benchtop DC power supply that we unboxed a couple weeks back, but what I know is that there's about 12 volts dropped on the input to the board when the downstream power supplies really kick things into gear. Now that could be enough to cause the hot swap controller to brown out, and that also could be why we're tripping the UVLO. Why the hot swap controller may not be recognizing the enable signal after browning out is a little beyond me right now, but either way, we'll never be able to finish the UPS power on sequence with a circuit fault like this. We'll never be able to finish the power on process with the repeated, interrupted, constant interruptions when the downstream load is being powered on. That load will consume any energy we were able to transfer in the short time before the error happens, and that may require more bulk on the input side of the power supply of that hot swap controller. More bulk would translate into smaller voltage dips on the board due to the peak loads, but there's only one problem with this solution. Adding capacitance upstream of the hot swap controller creates a mechanism for inrush currents while our relays are switching, and that will lead to arcing on the contacts. This arcing at the contacts will result in a shorter life of our relays and defeat the whole reason we wanted to put this circuit on the board in the first place. I'm really curious to see how this one shakes out after we find the root cause for the issue, but I could really see this turning into a 1-2-3 punch that completely eliminates the benefits of the hot swap controller circuit. That would just cause us to exit out of the architecture and move the functionality to the other blocks. Despite how the theory sounds, what we've just described is completely unacceptable performance. The whole point of this project is to reduce the number of times that our downstream systems power down unexpectedly, not increase it with nuisance trips. And nuisance trips have turned out to be a huge problem for this hot swap controller in our UPS design. Thankfully, the circuit isn't providing any functionality that we can't find elsewhere. While bring-up testing has exposed some serious cracks in our implementation of this circuit, every function that this circuit performs has been downgraded from a need-to-have to a nice-to-have. This decision was made because 3 key features can be performed with the other monitoring present on our board and a little bit of logic in our microcontrollers. One of these features is that inrush current limiting and electrical switching. Our 11 volt to 250 volt boost converter can take on these functions by disabling the power supply, the DC to DC converter, that will drastically decrease load level, which will decrease the load on our relays while switching and reduce the arcing in those contacts, as well as reduce the risk of welding relay contacts together. Another feature we can implement elsewhere is the UVLO. Since we already have battery monitoring in the application microcontroller, we can set a software threshold of 11 volts. Whenever the batteries dip below 11 volts, we'll know that it's time to power down. The third feature is the software circuit breaker, and that function can be taken on by a combination of the fuses scattered throughout the design and the inverter output monitoring itself. While DC power monitoring is great, monitoring the AC output voltage and current would tell us everything we need to know. We can use this power, this output power, to gain a pretty good idea of how much power is flowing on the DC side of the board using the typical efficiency of our converter. After all, We did design it, so we have the calculations required to figure out the efficiency based on load level. Depending on how large the output current becomes, we'll know that at some point we need to power down the input to really prevent damage or blowing a fuse. Powering down the inverter will decrease the load everywhere in our UPS, including the DC bus where the hot swap controller would have disabled the power. If worst comes to worst, we'll just shunt the hot swap controller out of the design and do exactly what we just described, move those features to other parts of the system. Even if the circuit isn't working the way we'd like, there is still plenty of time to debug this hot swap controller, mitigate the problems that we've found, and get this system back up and running. We've received our UPS boards from China, built a couple UPS systems, and now we're ready to keep our testing going. We're cruising through Bring Up, so subscribe to be notified of our future videos, where we will introduce the concept of electrical isolation with a crash course and discuss why we chose 32-bit ARM processors to power our design. I am super excited to have some of these prototypes in the lab, and if there's something you'd like to see us do with these UPS prototypes, let me know by hitting the like button on this video, giving us a shout on Twitter, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying till the end. Bye!